It's going to go in order. We're going to go ahead and start with 2-3. I thought 2-3 was super easy. At least the first question is. I can remember doing it. Large national bank determines that each of its branches is profitable or non-profitable. Additionally, the location of each branch is classified as urban, suburban, or rural. A summary of the profitability and location type of a random sample of 175 in the bank's branches is shown in the table below. From the sample of 175 branches summarized above, what proportion of branches are profitable? So if we're talking about profitable, we're just going to total that column up. And I'm going to go ahead and write the totals of all of them so that you have them. So 121, 54, 81 urban, 61 suburban, 33 rural, which is a total of 175. And all I did was add those up. So don't make it look like I did something special. Is everybody good? All right, so profitable. We're looking at the entire profitable. It didn't say specifically urban, suburban, or rural. So all profitable is going to be 121 out of the total 175. And every answer that they're given, they're doing 4 decimal places and not changing it to a percentage. Does that make sense? So you don't have to put it as a percent at all. Proportion, if you see proportion, it's going to be the point. If you see percent, then go ahead and change it to percent. Okay. What proportion of branches from an urban location are profitable? So urban, all of those that are profitable are going to be 64 out of not 175, out of 81. We'll give you 0.7901. Any questions on that one? So how would I set up the next one? The proportion of branches from a rural location that are profitable. 18 out of 33, which gives you 0.5455. Any questions? That's it. Super simple. All right. So the next one says, assuming the conditions for inference are met. So on these, you always need to write your hypotheses. Okay. So always make sure that you jot that down if they ask you. So assuming the conditions are met, does the data provide convincing statistical evidence the profitability and location type are independent for the bank at a 5% level of significance? Complete the appropriate inference procedure to support your answer. So you can write it 2 ways. Your null can be no association or not independent. I just like it this way because it makes me think about it a little bit easier rather than independent versus not independent. And your alternative is there is an association. We have categorical variables. So what are we going to use? What's this? Chi-squared. Chi-squared. And you may want to write that down. We're using chi-squared because of categorical. All right. So if you forget what you're doing, what's good is that when you look for your chi-square, which is underneath stat and over at test, stat over at test, it'll tell you what you need. So I know I need to do a matrices of observed and expected. Okay. So your observed are what's in your chart. So that's always what that's going to be. Your expected, how do you find your expected values? Row times column total over table total. Okay. So again, for your observed or your matrix A, that's a B, sorry. Your observed. You're putting in your 64, your 39, your 18, 17, 22, not 20, yeah, 22 and 15. For your expected, and I'm not going to write all of these out, I'm just going to show you the first couple. 81 times 121. So your row and your column total, you're going to multiply together, divided by your table total. Okay, and you can do that within your matrix instead of doing the work and then implementing it into the matrix. So your next one, your row total is 61, your column total is 121 over 175. And then your last one is going to be 33 times 121 over 175. And then you will do the other side as well. You will edit your tables 3 by 2. There's your A is your observed. Your B, when you put them in, they will give you decimals. And like I said, when I went right here, even if I clear it out, I did 81 times 121 over 175, and it'll put that decimal in for you. So don't, you know what I'm saying, don't do the work and then put the decimals in. That's too much craziness. All right. So stat tests, chi-square, we got our A, our B, and we're going to calculate. And then I'm going to write down what I got. I want to make sure I write both of these down if I'm working this out in my calculator. Got it? You want to write down what you're doing. You're doing your chi-square test. You got a chi-square value of 7.76. A p-value of 0.02. And you can put a 1 just to put it in there. It doesn't matter. And I know I'm going into number 2, but we're not going to do the work on here for just a minute. To come to a conclusion, you're going to compare your p-value to your alpha. Your p-value is 0.021. Your alpha is at 5%, so 0.05. 0.2 is less than 0.5, so what does that mean? Reject H sub O. Which means we have convincing evidence of an association, so they are not independent. So we have convincing evidence of an association, and make sure you do it in context of the problem. So not independent. And again, in context of the problem. Any questions? Is everybody good? All right, so I'm gonna flip the page. I thought that one was pretty easy. Just got to remember it's a chi-square because of categorical variables and what you need to put in. Describe the association shown in the scatter plot. Okay, put it in context of the problem. Strong, positive, linear. What else? Anything else? Shape center spread. A possible outlier. At, I said 4,000 feet squared, comma, $500,000. Very good. That's it. That's all you need. Just make sure you identify outliers or anything that's weird from the data. All right, so I'm not going to make the graphical display. I'm going to show you what they do, and I'll show you why they do it that way. All right. So what they have is your expensive 8.4 and your total 12 to 16.18, whatever. And it wanted you, blah, 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 use information in the table to construct a graphical display of the data. When we make our display, they do a stacked bar graph. And they started with not large, and your not large was 2 out of 18 and 16 out of 18. So 2 out of 18 will be your 11%, and then your 89% is the other one. So they both should be out of 100 because there's 100%. And then same thing on this one. You had 8 out of 12, which will be your 67%, and then 4 out of 12, which will be your 33%. Just make sure, it doesn't matter. You could have stacked them the opposite way, so the darker ones could have been on top. It don't matter, just as long as you label everything and make a key. Okay, so that's the thing. If they ask you to graph or design a graph, make sure you label it and put a key. Is everybody good? All right. For the next part, and it's blocked off, it actually goes to the next page. Assume there's no association between size, large or not large, and price, expensive, not expensive. Use the given totals to complete the following table with the expected number of houses for each classification if there was no association. So how do we do expected number? So if we're looking at this table right here, to get this first number, you're going to do your row, which is 10 times 12, and divide it by your table total, which is 30, which gives me 4. You're going to do the same thing for the other one. 10 times 18 divided by 30 gives me 6. If you need to write that in there, go ahead and do that. Is everybody good? The other two going across from left to right are 8 and 12. And that is that part. So for associations displayed in the scatter plot, the strength of the linear association is measured by the correlation coefficient, or R. So this R is 0.82. For associations that are summarized in two-way tables, the strength of association is measured by the chi-square statistic. The formula for the chi-square statistic is blah, blah, where expected is the count, assuming no association observed is the count shown by the data. Greater values of chi-square indicate stronger associations. For the table counts in part B, chi-squared equals 10. Suppose the selling price for the most expensive house in the sample is decreased from $489 to $325. So if I go back, and I hate that these are on different pages, but so this most expensive house is at $489. Remember we said it was right at 500. Is decreased to, what did it say, 325. So like right here. So this would go away and this one would come in. What would it do? What would it do? So what effect would the decrease have on the value of R? And remember, R is the strength of the line. Think about that slope. So that outlier, try to put it up there together. Okay, the outlier is pulled down to right here. Remember, we're talking about the line of best fit. So the line of best fit, remember, is going to be pulled towards outliers. So what would happen to that line if we took that outlier out? It would flatten out, right? So what happened to the slope? Less. So that's all it's looking for. It would decrease. And then why? Oh, my answer's up there. Sorry. It would decrease. Why? pulls it back where we took the outlier out. Towards what? What's the littlest R that we can have? 0. That's the least association. Remember, as we get to the negatives, it gets stronger towards -1. It's just a negative association. All right. What effect would the decrease have on the value of chi-squared? And explain your reasoning. Think about it. What do you use, and don't tell me observed and expected, what do you use to get chi-squared? Do you use the actual value of the house, the actual data? How do we get the chi-square? Did value of the house come into play when we were doing chi-squared? How did it? Why are you saying no like that? Why are you questioning it? It may be the way that I'm asking it. I'm not trying to be. Okay, so like when we talk about R, what goes into making R? Do I? Okay. Look at your.
We didn't use the price.
Right. It's just how many houses are in that price range, right? Right. So your chart that we use for chi-square just uses how many values are in there, how many dots are in that little range of values, where your R value uses the actual price of the house. Does that make sense? So what you're doing is kind of grouping these dots together when you do that. Maybe these dots are in that not large, but expensive. You know what I'm saying? So when we're talking about the chi-square, we're not using a value. We're not using a value. Okay. We're only using a number. So think about it like mean compared to median. Mean compared to median. Do values, changing values, change the mean? Yes. Do changing values change the median? No, because if we had a high value, if there, yep, resistant or non-resistant. Okay, so think about it in that way. So the value makes it not resistant to change. Okay, so what we're looking at here is this chi-squared will not, nothing will happen, because that house, that particular house, is still large and expensive. It doesn't follow through with the value. Is that better? Make a little bit more sense? So think about it in like the mean and the median sense. It doesn't matter if we're finding the median, that last number outlier could be 100 or it could be 1,000,000, and it's not going to change the median. But as we change that value 100 to 1,000,000, it will change the mean. Does that make sense? Because it's based on the value. Okay. All right. Based on your answer to part C, explain one benefit and one drawback of using chi-squared rather than R to measure the strength of the association. So tell me a benefit, and I'm going to put one up top and one below. So benefits. So what's the benefit to it? You got to compare it. That's what I'm saying. R is what? Okay, so make sure you compare them when you answer it. What's the drawback? What does it not use? What did we just talk about? So chi-squared doesn't use value. That is lost in the generalization. Okay, so chi-squared doesn't use that value, so it's lost in the generalization. So that house could be way more expensive than every other house on there, but we'd never know because it's just big and expensive. That's all we know. That makes sense. So if you're looking for a house And you can say, I can afford things in this big and expensive range. If you can afford it, which one would you rather have? The biggest one, right? Rather than the smallest one, but we don't know which one that is because it's just generalized into big and expensive. Okay. All right, number 3. This is the one that was on that other one. To prevent deer from running across highways, researchers are investigating sound emitting devices that would frighten deer before they reach the highway. As part of the investigation, the researchers set up 20 devices along a 2-mile stretch of road. When a deer approached the device would activate and emit a sound. The researchers recorded whether the deer moved toward the highway, a positive response, away from the highway, a negative response, or did not move, a neutral response. The researchers kept the loudness of the sound constant at 60 decibels. However, they varied the pitch of the sound. There were 6 treatment levels, all measured in kilohertz, 0, 0.28, 1, 8, 15, and 28. The order of the treatments was randomly assigned. All right. The control in the experiment was 0 kilohertz or no sound. What information is gained by using the control with no sound that could not be obtained if no control were used? Why do we use a control? Well, what you're doing is, if there's no sound, we can see what they do, right? When we put a sound, does it change? You see what I'm saying? So we're going to determine if the sound made a difference at all. Why is that the case? Think about it and I always think in medical terms, like if we all take pills, but we don't have a control, how will we know they work? What could be happening? What could be happening? So I take a pill and my body changes. Something in it changes. What could be happening? What could be happening? Yes, you do. Is it necessarily the pill making it change? It could be what? Like what? What's it called? What could be the difference in me taking it and you taking it? Yeah, I'm old. Y'all are not. Y'all understand that? What could be the difference in me and Ben taking it? Regardless of the old, young. Yeah, he's male and female, right? So compounding variables change those things. So if we have a control, this 0 sound, we want to see what they do before the sound is even there. Does that make sense? Do they run towards the highway? Do they run away from it? What happens? Then when we add the sound, what happens? Okay, so we want to make sure that we control for it to determine if sound makes a difference at all. Again, you can compare, and I'll go ahead and write this down so you can see it too. You can compare the 2 sounds, or 3 or 4, whatever. So 0 compared, not the 0, but the 0.28 compared to the 1, the 8, the 15, the 28. You compare the 2 sounds. And determine which is more effective. But not if it works. Compared to no sound. So you have to have that control. So again, when you watch those commercials and they're like, we're looking for people 18 to 25 males that have done this and this and that, that's what they're doing, is they're getting rid of those compounding variables so that when they give the control, they know it's not anything, that's their control. They don't have any compounding variables in there to mess up the experiment. All right, what is one advantage to keeping the loudness at a constant 60 decibels for all treatments? What did we just say? Reduce compounding variables. What is one disadvantage to keeping the loudness at a constant 60 decibels for all treatments? What can we only make a conclusion about? Absolutely. So we can only conclude based on the 60 decibels and no other loudness. Very good. All right, so here are your results of the experiment. Based on the results, would you recommend using a sound emitting device to keep the deer from running across the highway? And explain your answer. So I'm gonna go back real fast and remind you what they were. Okay, 'cause I don't even remember. That's okay. The highway running towards the highway is a positive response. So going to the highway is a positive. Away from the highway is a negative, and no movement is neutral. What do you see?
It didn't really make you go away.
It didn't. If we look at our control, which is right here, how much do they differ? Yeah, and they really don't differ that much from each other either, do they? So when we're looking at this, based on the results, would you recommend using a sound emitting device to keep deer from running across the highway? Why?
There's enough negative results to put them all up every day.
Not enough change. And it doesn't have to be negative, it can be positive too. You know what I'm saying? Like we could say, okay, yeah, no, we definitely can't use them, or yeah, sure, we could use them. But this one says, since there's not much difference in control, we can't conclude or recommend. Since not enough change, no conclusion to be made, no recommendations. Very good. Any questions on 2-3? And again, 2-3 and I think 3-5 were the same. So if you're wondering why we don't go over that last free response number 3 or in unit 3, that's why these two were the same. So it's that same question repeated. All right. 2-8. I was just lazy and didn't read it. I didn't even read anything at the top when I did this, and it was fine because you could go it without it. Is a linear model appropriate to use for these data? Justify your response by referencing the residual plot. No clear pattern in residual plot. Okay. The only time I had to reference back to the problem was to interpret or to even see it. So American beavers are foragers with a central home location that make foraging trips from their lodge to and then return. To test the optimal foraging theory, researchers trapped and radio tagged a random sample of 67 American beavers from the population in a certain region and recorded their movements over the course of about a year. The researchers fit a least squares regression line to the data where the explanatory variable was distance to the lodge, so your x was distance in meters, and the response variable was speed in meters per hour. Okay, the resulting residual plot was shown. All right, so then they made the chart so that they could get the linear model. And I'm not quite sure what the box plot is for, but it's there. Okay. So it says identify, and oh, I know what it's for. It's from further on. Okay. Identify the intercept of the least squares regression line and interpret it in context of the data. So the intercept is like where you start. All right. So which number up here is the intercept? What do you think?
-60.
Yeah. Yeah. And it says intercept and goes from there. Got it? All right. So it is negative 16.462. And this is in context, not in context of the problem, but with units meters per hour. So what is this? It's where he starts. So when we look back, what we're talking about is how fast they move and how far they move. So how far he moved was nowhere because he's at the lodge. Does everybody understand that? So that's where he starts. So this is the predicted speed. And you always need to use the word predicted because that's exactly what a line of best fit or a regression line is, a prediction line. It's the predicted speed of a beaver at the lodge. They didn't go anywhere. And we know that we can't have a -16 speed, but that pretty much tells you that they're not moving. Is that good? All right. The researchers plan to calculate a 95% confidence interval for the population slope. Identify and check the conditions for the appropriate confidence interval for the population slope. So remember for this one, you have to check the liner. Okay, so the liner. Okay. L is for linear. Was it linear? And you will have to write this out, but we're going to talk about it. And if you want to write it out on the side note, that's fine. Was it linear? You already know this. We've already answered this. Because why? Yeah, the residual plot doesn't have pattern. So we already did that. So is it linear? Yes, the residual plot has no pattern. What about independent?
Yes.
Why?
No, just checking.
What do we do for independent? Hmm? 10%, right?
Yeah.
So what was our sample?
67.
Uh-huh. You think there's more than 670 American beavers?
Yeah.
Yeah. So that one's good. What about normal? Look at the top of my screen. The box plot is? How do you know? It's not skewed, so it's roughly symmetric, right? With no outliers. Got it? So we know it's normal. Remember, the E stands for equal scatter. So when we look back at the residual plot, it's pretty equal. You guys would know it'd be really weird looking. Okay, so we're good. And then what is R? Equal scatter or equal SD, equal standard deviation. R is random. Was this random? They tagged a random sample. So that's it. But just make sure that you write it out for each one. Okay. So use your acronym liner, but then write it out for each one. All right. Next. It says the 95% confidence interval for the population slope was calculated as 0.751 to 0.947. Based on the confidence interval, do the data provide convincing evidence, statistical evidence, that foragers with a central home location move faster the further they are from the home? What? Yes. What would 0 mean? That what? Is not included. In the interval. Very good. Any questions? Again, what does that do? That shows that their relationship. And you do want to write that. In context of the problem between blah, 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 distance and speed. Everybody good? All right, show all of your work indicate clearly, blah, 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 blah. The following scatter plot shows the number of wins and the attendance per game for 30 baseball teams in 2017. Also shown are the least squares regression line and the computer output. Let's flip my page over so you can see it. Looks like this. Got some output down there. I thought these were pretty simple as well. Interpret the slope of the least squares regression line in context. So what's the slope? It is 235. So we're talking about number of wins and attendance per game. So what is the slope in context of the problem? So your slope is 235 over 1. This is how I like to teach my math 1 kids, just in case they talk about interpret the slope. Remember, it's the change in y over the change in x. Perfect. So for each game, and they like the word additional game, $235 more people are in attendance. Or it increases by 235. Explain why it's not reasonable to use the least squares regression model to predict attendance per game for 0 wins. Yep. Until 60. Predicting outside the data, which is called extrapolation. Very good. See, you do know. Y'all know this stuff. Don't care. Don't care. Y'all got to stop overthinking. Like I said, I thought this section was fairly easy. All right, what is the value of the correlation coefficient for the sample? What represents correlation coefficient? It is R. What do they give us in the chart? They give us R squared. So we have R squared equals 12.29 or 0.1229. So we're going to take the square root and we get R equals 0.3506. That's literally it. So you're going to have questions that are going to be very simple like that. Don't stress out if you can't get one part, because you can get, like this would give you a 4 on that part, where this one might give you a 2, which would average out to a 3. So it's not a huge deal. Okay, don't stress about it too much. All right, part D. If the point representing 64 wins and attendance of 40,786 people per game is removed from the sets, I'm going to show you that while we're looking at this. All right. So 64, that's not the right one. Sorry, this one is though. So 64 and 40,000, which is this one. We're going to take that one out. How would the following be impacted? Explain your reasoning. The slope of the least squares regression. These are basically the same question as before. What's going to happen to this line? What is this dot doing to this line? Tell me exactly what it would do. It's pulling this end up, right? So if I take it away, what's going to happen to this end? So think about like a seesaw. It's pulling it up, but now when I take it away, it's actually going to make it go like this, right? So what's going to happen to it? The slope will be steeper or increase. And again, because it pulls what? It'll pull the low end down towards 0. Okay, and you can write that on there too. What about the correlation coefficient? What do outliers do to the correlation coefficient? It makes it weaker, right? So if we take those outliers out, what's it going to do? Yep, and why? Because we take the outliers out. We're going to make it closer to 1 or stronger. You can say stronger because we're eliminating an outlier. That weakens the correlation. All right, any questions on that? Okay, this one's not terrible. All right, a recent study reported that high school students spend an average of 94 minutes per day texting. Jenna claims that the average for the students at a large high school is greater than 94 minutes. She will conduct a study to investigate this claim. To collect data, Jenna will select a sample of size 32 from the population. State her population of interest. All students at Jenna's high school. Very good. Name and describe a sampling method Jenna could use that will satisfy the conditions needed for inference to the population. We did this like very first. She could. We can make it even easier than that. Let's just do a regular simple random sample because we know how to do that, right? There's a bunch of different ways that we could do it too. What are the different methods that we could use to do an SRS? Yep. So just make sure when you do this, you could do hat method. You could just do a list of names with a random integer function on your calculator, but remember you have to literally like spell it out. Okay. So list of names of all the students, put in a hat, shake it, pull out 32 without replacement. Those 32 will be used for the sample. That makes sense? So make sure you say all of that. If you don't, you're going to get partial credit for it. Okay. All right. Based on the sample of 32 students, Jenna calculated that the sample mean is a sample mean of 96.5 minutes and a sample standard deviation of 6.3 minutes. Assume all conditions for inference are met. See how real nice they are? They're, you know, if they ask you to do conditions, it's like in one of its own questions, but if they're doing a full one, you don't have to. But what do we got to remember to put in here? If they ask you to do an appropriate inference procedure. Your hypotheses, make sure you add those all the time. So you just skip that second step, the plan. Sorry, there should be an O. H sub O. So H sub O is what? She said that it was greater than 94. So what is our null? That the mean is equal to 94. Your alternate is that it's greater than 94. All right, so we're talking about means. So we're talking about means. What test are we using? You are correct, a t-test. We've already did chi-square. When do we do chi-square? For categorical. So means is t. So what's, say it again. What is? Proportions, RZs. Okay, so how do you know which test to use? Right there's your answers. You do know which ones they are. Just listen to your paper, okay? Your t-test is what we're going to do. You can remember, you guys can write these anywhere. They grade the whole paper, so it doesn't matter. All right. We're trying to find the probability that X is greater than 94. How do we do this? How do we do this? What are we doing? Where's it at? Where? It is stat. Over to your test. We're going to go down to a t-test. If you need to write that on your paper so you remember where it's at, that's fine. We're going to do stats because we know them. Our null is 94. What's our mean?
96.5.
What's our standard deviation?
63.
What is our n?
32.
32. I would write all of that stuff down. So I would even be spazzy enough to write stat, calc, t-test. This is what I put in. And then we're going to calculate, but we want it to be greater than, right? That's our alternative, greater than. Everybody good with that? And then we're going to calculate and we're going to write all these down. So we're going to write that our t value was 2.24. Our p value is going to be 0.016. Our x bar is 96.5. Our standard deviation is 6.3. And our n is 32. We want it at the alpha equals 0.05. So our p value compared to alpha, 0.16 compared to 0.5. Not O, is that 0.16? Yeah. What do we get? Okay. Is it? I got 0.016. Alpha is great. I thought you
I
said.
was like,
I'm so sorry.
I was
thinking
not
great. I was looking
right.
left to right. I was looking left to right. I was looking left to right. I
I
apologize.
was sitting there like,
Oh my
it's
gosh.
not that I don't know the answer.
Because I was thinking less than in my head because I'm reading left to right and you're reading right to left. It's okay. You're good. What's this mean? Reject H sub O, which gives you what? We do have convincing evidence that what? The average for the students at her large high school is greater than 94 minutes. The average minutes per day of texting. You got that? So in context of the problem, just go back up to the problem and rewrite what it says. Okay. That's all I want on that one. Everybody good? Pretty simple, not too bad. All right, let's go ahead and finish this one, and then y'all don't have to listen to me anymore for a couple days. All right. Biologists want to estimate the number of deer living in a certain region. They will use a method known as a hair snare. Y'all know what that is? Where it literally snags their hair off their back or whatever off their body. So it's like a tuft of hair. Okay. A hair snare is a length of barbed wire set up near a salt lick where deer can lick minerals and nutrients from salt deposits. The wire snares the hair from the neck of the deer. The hair is collected and sent for analysis. The biologist will randomly place 90 salt licks throughout the region. The region consists of 3 areas: the town, the forest, and the lake, as shown in the following diagram. 2 methods have been proposed for choosing where to place the salt licks: a simple random sample or a stratified random sample with the area a strata. Give one reason why the stratified random sample might be the better method for choosing where to place the salt licks. You get an accurate representation of all areas. And then explain why it would be more accurate. Since what? Since why?
They might not follow all of them.
Okay, well, let's think about your 3 areas.
Oh, they're not gonna be in the town that much.
Since may have less in town. Compared to other areas. And that could be anything. There may be more in the forest hiding out, or there may be more at the lake because they're drinking water. Y'all understand what I'm saying? So we want to get a stratified to make sure it's more like the overall population. We want some from every area. All right. By using the hair snare method, deer are sampled with replacement. Why is sampling with replacement a problem in this context, and how would the problem impact the estimate of the number of deer living in the region?
This is not the same deer.
Yep, may catch same deer. And record data multiple times. Very good. And that's it. Is everybody good? Any questions? All right, I'm gonna stop sharing, stop recording.